Before we can get into that, we need to talk about light. So we need to learn a little bit of physics. Physics and chemistry overlap, just like all sciences overlap with each other. So light is a form of electromagnetic radiation. It's composed of perpendicular oscillating waves, one for the electric field, one for the magnetic field. So an electric field is a region where a particle that has an electrical charge on it will experience a force. Magnetic field, region where a magnetized particle experiences a force. So all electromagnetic waves move through space at the same constant speed. And that speed is 3 times 10 to the 8th meters per second. And this is often called the speed of light because it's the speed that light moves. Right? How fast is that? That's equivalent to 186,000 miles per second, which is fast enough to circle the Earth 7 times in 1 second. I mean, if you had a globe and you're trying to move your finger around the globe 7 times in a second, you'd kind of have a hard time doing that. But this light can actually go around the Earth 7 times in 1 second. I mean, it's just incredibly fast. So this is an illustration of those electric and magnetic fields. So the electric field may be going in this plane, it oscillates up and down, and then the magnetic field is perpendicular to it, but their nodes correspond. And they'll be traveling in the same direction at the same speed. This is a picture of a lightning strike. So lightning strikes this building, and we know that thunder happens when lightning happens, right? So if we're far away from this, we see the lightning strike, and then a few seconds later, we hear the crash, the thunder. That's because the sound is moving at 340 meters per second, while light is moving at 3 times 10 to the 8th meters per second. Much, much, much faster. And so you may have heard, I always forget how many seconds it is per mile, but you can figure it out. So you see lightning, hit something, and then you can count the seconds until you hear the sound of the thunder. And that will tell you how far away that lightning strike was. And that's just based on the difference in the speed between the sound and the light. So there are a number of characteristics of waves. So here we have an illustration of a wave. We can talk about the amplitude. That's how tall the wave is. This is a measure of how intense the light is, how bright it is. Larger amplitude, brighter light. We can also talk about the wavelength. So this is the length from the peak of one wave to the peak of the next wave. And wavelength is going to be related to, for visible light, to the color that we observe the light to be. So here we have 3 different wavelengths of light. They're all traveling at the same speed. This red light has a longer wavelength. The yellow light is sort of in the middle, and blue light has a shorter wavelength. Our eyes interpret different wavelengths of electromagnetic radiation as different colors. And here is comparing amplitudes. So a dim light would have a low amplitude, a bright light would have a high, large amplitude. But the wavelength would be the same if they're the same color. So frequency is another characteristic. That's the number of waves that pass a point in a given period of time. So we could say that the number of waves is the number of cycles of the waves, and so the units would be hertz, which is cycles per second. Hertz is used for engines and refresh rates on screens and all kinds of other things. It's basically events per second. So hertz is 1 cycle per second, or sometimes just 1 per second, not really stating what the thing is. So we can think of this in relation to the ocean. So we're going to the beach, and we're going to Pismo in August, where it's 100 and gazillion degrees here. And why do we go to the beach in the Central California in the summer? To be cold, right? Because you go to Pismo, or maybe you've not been, you go there and it's probably going to be like 65, 70 degrees, overcast, and a strong wind, right? So bring your sweatshirt, wear your long pants, and play in the really cold water. There's a reason why it's mostly Central Californians in that part of the coast, because we don't want to be hot, we want to be cold. Anyway, so you go to the beach, you're standing on the beach, and, ocean waves come in. And they, maybe you're standing ankle deep and they come and they crash on your legs, right? So let's think about this. If the waves are really short or the waves are really tall, is that going to affect how they impact you?
Mm-hmm.
Yeah. If you go out there when there's a surf warning and they got really, really big waves out there, one of those waves could knock you over, right? So that's the amplitude of the wave. The higher the amplitude, the more energy there is. And the other thing that it affects the energy is the frequency. So with, let me erase one of these. So with light, the waves are coming at the same speed, and so the frequency is going to correspond, this is very ugly, correspond to the wavelength. So if these are moving at the same speed and you've got a shorter wavelength, these waves are going to crash on you more frequently, right? This first one, maybe you get hit every minute or every 2 minutes or something, and then these more frequent waves come in and they're hitting you every 30 seconds. Well then, even if they aren't that much bigger, just because they're constantly pounding on you, you might get knocked over and you just literally can't get up, because as soon as you start to get up, another wave comes on top of you, right? So higher frequency, more energy, okay? So when the waves are traveling at the same speed, the shorter wavelength means they'll hit more frequently. So the wavelength and the frequency for electromagnetic waves are inversely proportional. If the wavelength is long, then the frequency is small. If the wavelength is short, the frequency is high. And the speed of light is constant, and so we can see this relationship between frequency and wavelength. So this is frequency, and this is wavelength, and this is speed of light. The color of light is determined by its wavelength or its frequency, because wavelength and frequency are directly related to each other. So what we observe as white light is a mixture of all the different colors that are present in the visible light spectrum. So it's a spectrum, it makes a rainbow, right? We can separate the colors using a prism, and we see that there's this whole range of colors. They just run into each other, right? And the colors here are always in the same order, and this is the order: red, orange, yellow, green, blue, indigo, violet. It's helpful to be able to remember that, and the way I've always remembered that is Roy G. Biv. One semester I actually had a student whose name was Biv. That was kind of cool. So this is like somebody's name, right? Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. When an object absorbs some of those wavelengths and reflects other wavelengths, that is what we observe as the color. And so if we look at this woman, her red shirt is primarily reflecting red light and absorbing the other colors. Blue jeans, reflecting blue light, absorbing the other colors. Black hair, that's absorbing pretty much all the color. And that's one of the reasons why, like if you have a black lab or a black cat, it's really hard to get a good picture of an all black animal, right? Because they just absorb all the light. And so they tend to just look like this black blob in pictures, unless you're really, really good at photography. Okay, so let's use that equation and do a calculation. So a laser dazzles the audience at a rock concert by emitting green light with a wavelength of 515 nanometers. Calculate the frequency of the light. So they're giving us a wavelength and asking us to find the frequency. So this is one of those problems that requires an equation. So the frequency is equal to the speed of light divided by the wavelength. So they tell us what the wavelength is. The wavelength is 515 nanometers. And c is a constant. C is the speed of light, 3.00 times 10 to the 8th meters per second. That's one of those things that I'll give you on the information sheet for the exam. So we're trying to find frequency. We know what the speed of light is and the wavelength, and so we can just plug those numbers into this equation. We should always, 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 always write our units. And before we bother calculating, let's look at the units and see what's going to happen. Is meter going to cancel nanometers? No. So we need to get them to be the same units so they cancel out. Well, I think the simplest thing is to write this with, instead of nano, what it means, which is 10 to the minus 9. So nano, like 90, 10 to the minus 90 meters. Now the meters are going to cancel out, and we're going to end up with a unit of 1 over seconds, which is a unit of frequency. Okay, 3 times 10 to the 8th. Oops. Divided by 515 times 10 to the minus 9. 5.83 times 10 to the 14 per second. We could also express that as hertz. 5.83 times 10 to the 14th hertz. Any questions? So, visible light is electromagnetic radiation. That's only a little tiny part of the whole range, the whole spectrum of electromagnetic radiation. So, shorter wavelength radiation, higher frequency, has higher energy. And examples of higher energy radiation would be gamma rays. If we have longer wavelengths, lower frequency, then we have less energy, and radio waves would be at the other end of that with the lowest energy. The really high energy electromagnetic radiation has so much energy that it can damage biological tissue. It can cause a molecule to become an ion. Well, then that molecule is not going to undergo reactions in the same way that it did before, and so that can be very disrupting for life. This is called ionizing radiation. Okay, so this is the figure from the textbook, the electromagnetic spectrum. So at the top we have a line showing the frequencies in hertz, and here we have a line showing the corresponding wavelengths. You'll notice as the frequency gets bigger, the wavelengths get smaller, because that's that inverse relationship. And here we have the names of different regions. So this part right in the middle is visible light. Higher energy is at this end with higher frequency. So we've got ultraviolet, X-ray, and gamma rays, and on the other end, lower energy, infrared, microwave, and radio. Now, what's sometimes confusing about this diagram is we have this big rainbow down here, and sometimes students try to line this up with these other scales here, and that's not correct, because all of this, let's see, all of this comes from right in there. We've just zoomed it out so that you can see it, because this is part that we're often interested in, the different colors, what their wavelengths are. But violet light does not have the same energy as gamma rays, thank goodness. Violet light is over here. So don't get mixed up when you look at that. So you should read about microwaves, infrared, visible light, ultraviolet, and X-rays. There's little blurbs in the textbook about that. And notice here we have that order again: red, orange, yellow, green, blue, indigo, violet, Lord G. Biv. So we can use a prism to separate light based on its wavelength. Different wavelengths will bend differently in the prism. And so from white light, we get a continuous rainbow or spectrum. This is thermal imaging using infrared light. You may have heard of night vision or heat vision. How do they use technology to see at night without shining lights on things? Well, warm objects give off infrared radiation as heat. And you can develop a sensor that can detect infrared radiation. Our eyes don't do that, but you can make a sensor that does. So this picture is from a field trip I got to take with my daughter to NASA's Jet Propulsion Lab down south. So this is us viewed on a regular visual camera, and this is on the infrared camera. And so what the computer is doing is taking places where there's more infrared radiation, and it's showing those as red areas, and less is blue. And so you can see where our skin is exposed. You see this red-orange color, and you see my phone is pretty hot because I was taking lots and lots of pictures, right? So you can use a camera like this, and you could look into the woods, and you can see somebody hiding because they're warmer than the surrounding bushes and stuff. Kind of cool. High energy radiation, like gamma rays, can be used in productive, helpful ways. One way that they're used is in radiation therapy to get rid of tumors, usually cancerous tumors. The trouble with this is, say you have a tumor in an area where you can't just operate and cut it out, because like if it's in the middle of your brain, you'd have to damage the surrounding brain tissue to get it out, and that might be worse than just having the tumor. But what we can do here is we can take radiation and focus it on the tumor from lots of different directions. They'll actually just, kind of rotate around, and not just in a big circle, but all around, and hit that tumor from all different directions. So the healthy tissue around the tumor gets a small dose of radiation, which isn't great for it, but doesn't do much harm. But the tumor itself gets a lot of radiation, and you can shrink the tumor or sometimes even kill it completely. So that's kind of a neat thing. So another thing that waves do is they can interfere with each other. They can do this constructively or destructively. So here we have two waves that are in phase with each other. So that means that their peaks line up with each other. And so when these guys run into each other, their they basically add. And so the amplitude gets much, much larger. That's constructive interference. Destructive interference happens when waves are out of phase. So here you have the peak of one lined up with the trough of the other, and when you add these, they'll add up to zero. And basically the waves are canceling out. Just make them disappear. This is the idea behind noise canceling headphones and earbuds. Is we have the technology now to take the sound that's coming to your ear and shift it very slightly so that it becomes out of phase and play it back through the speakers, and it will cancel the incoming noise. If you've ever used those headphones, it's really pretty amazing. We also see effects like this bouncing on a trampoline with another person. If you've ever been able to do that. Sometimes, you're bouncing along, and sometimes, you're expecting to bounce a certain height, and you just, stop. How did that happen? Well, that was destructive interference between your bounces and the other person's bounces. And other times, you just get sent really, really high, and you're like, wait, what happened? That was constructive interference of the waves on the trampoline. Diffraction is when traveling waves encounter an obstacle or an opening in a barrier, they will bend around that obstacle. Traveling particles don't do this. They just travel in straight lines. And we're going to get more illustration of this because this probably doesn't make a lot of sense right now. But the diffraction of light through two slits can result in an interference pattern of the diffractive waves. And this interference pattern is characteristic of all light waves, all electromagnetic radiation. So this is what that looks like. So wave diffraction, waves come and they hit this barrier and there's a slit in here. The waves that get through the slit are bent. So they're not straight anymore, they bend. Particles, when they encounter a slit, they either go through the slit and continue on their same trajectory, or they hit the barrier and they don't go through. So particles behave like this and waves behave like that. This interference pattern happens when you have two slits that are close to each other. So here we have a single light source. It's sending out radiation. All of that radiation is in phase because it came from the same source. So as it hits this slit and it hits that slit, the radiation is still in phase. The waves are in phase. They diffract as they go through the slits, still in phase. And now as these diffraction patterns, the diffraction waves spread out, they're going to start interacting with each other. And there will be some places where the waves are out of phase and they cancel each other out. And so there we'll see dark spots. In other places, they will be in phase and make bright spots. And then there's, kind of in between where they kind of cancel or kind of reinforce each other.
Every Aetna CVS Health individual and family plan comes with the Aetna network of doctors, specialists, and hospitals. From maternity care to mental health and more, you get the quality care you need in your community, all at an affordable price. Learn more at aetnacvshealth.com.
What is light?
What is light? What is light? That's a good question, isn't it? What is light?
Isn't it an element?
Light is brightness, I guess.
We have auras,
We all have auras.
which are light.
Yes, they are.
It lights up the room. It makes it not dark.
What's the difference between blue light and red light?
The colour.
It goes in your eyes and then we see stuff.
They range from white to red to orange to green. It's like the chakras of your body.
Can you see my aura?
No, not particularly right now.
Is it too bright out?
It's very sunny out here today.
Does that make it harder to see someone's aura?
Not necessarily.
If I was to explain it to a blind person, right,
Yeah.
it would be the difference. You see nothing whatsoever as a blind person, whereas I see things in front of me.
To be fair, the question of what light is not an easy one. For centuries, the greatest minds in science debated this issue. In the late 1600s, Newton proposed that light was a stream of particles, or corpuscles. He proposed this in his treatise Optics. But at the same time, a Dutch physicist named Huygens proposed that light was a wave. And this debate raged on until it was settled by the experiment I've recreated today, Thomas Young's double-slit experiment. To make sure I got the experiment right, I went to the original source. With the help of Brady Heron, I managed to get into the vault underneath the Royal Society in London. There I found Thomas Young's handwritten notes from 1803.
I brought into the sunbeam a slip of a card, about 1/30th of an inch in breadth, and observed its shadow, either on the wall or on other cards held at different distances, besides the fringes of colors on each side of the shadow. The shadow itself was divided by similar parallel fringes of smaller dimensions. Wow.
This is an experiment so simple that you could make it at home, and yet so fiddly that I have never seen it before done with sunlight.
I was thinking about doing it in a box, like a fridge box.
You can take it out on the street.
Taking it out on the street.
Could I possibly interview you guys for about a minute? We're doing a science experiment. I have here is an empty box. And this is a little eyepiece where we can look in, and this is a hole. And I'm going to place this slide above that hole. And if you look closely, you'll see that there's two openings. Very narrow openings side by side. It's a double slit. Now before we have a look, we need to tilt it towards the sun a little bit. So we want the sun to hit this double slit directly. What are we going to see on the bottom?
Well, the obvious thing you think you're going to see is you're going to see two lines.
2 lines on the bottom of the box. 2 bright bands.
Two little lines.
Yeah.
I think it'll be one line instead of two.
I can expect to see the whole box lit up.
That'd probably be a kaleidoscope of some sort.
A bunch of colors.
Probably, yeah.
Rainbow, different colours.
There, have a look. You expected to see kind of one line. Is that what you see?
No.
I see dots.
How many?
It's one circle.
Oh, there's one in the middle strongest, two either side.
The two on the outside are multicolored. The one in the middle is just white.
Kind of a rainbow.
The rainbow of colour as well.
Quite a few colours, but lots of little dots.
Like there are more dots appearing.
I think I can even see more dots spreading along. Yeah, that's amazing. Yeah, I can see tons of dots now. Not tons, but I can see dots spreading across that way.
Either side.
Yeah, definitely.
Isn't that amazing?
Yeah, that's incredible. And that's just nothing else apart from
2 slits.
2 slits. That's incredible.
But all we're doing is we're putting a light through 2 very narrow slits side by side. So how does this make any sense?
There's some kind of principle involved there. The average person is not familiar with. That's the only explanation.
No, I'm really confused by it, but I'd like to find out why.
People were debating, is light a wave or is it made of particles?
So what causes that?
Well, if light were behaving as particles, you would expect them to go through each slit and just produce a bright spot underneath. So we would see 2 bright spots on the bottom of the box. But if light's behaving as waves, then the wave from one slit can interact with the waves from the other slit. I've got a demonstration here on a little pond where we can see this with water waves. I have 2 sources of ripples, which are basically like the 2 slits. When I create ripples with a single source, they travel out with circular wavefronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern. This pattern is created by the ripples from the 2 sources interacting with each other. Where they meet up peaks with peaks and troughs with troughs, the amplitude of the wave is increased. That's what we call constructive interference. But if the peak from one wave meets up with the trough from the other, then we get destructive interference and there's basically no wave there. And this is exactly what was happening with the light. When the light from one slit met up, peaks with peaks and troughs with troughs, they constructively interfered and produced a bright spot. But if the trough from the wave from one slit met up with the peak of the wave from the other slit, they would destructively interfere and you wouldn't see any light there. It's light cancelling itself out.
This is basically the same as like having 2 drops of water fall in a swimming pool.
That's right.
Exactly the same
And then they go and overlap. As this ripple overlaps with those ripples, down the bottom, you get a series of, you get like a bright spot, and and then a dark spot, and then a bright spot, and then a dark spot, and then a bright spot.
Now, there's a slight complication, which is that sunlight is composed of many different colors, and they have different wavelengths. So obviously they're going to meet up at slightly different points. And that's what caused the rainbowing effects as we go further from the central maximum. So you saw the ones to the right were slightly colored.
Yeah,
that's
it's
because
working.
the reds are going to meet up at different places than the blues.
And that's all that makes the colour differences in different wavelengths.
Exactly.
That's amazing.
So the difference between red
So
and blue,
that red bin over there, the green part is just, I'm seeing
It's a
that,
different-
it's just different
different
wavelength. And that's how we bring in all these beautiful colours all around us.
exactly.
That's amazing. I'm amazed. Oh, good on you, thanks,
Hey,
Ben.
thank you.
I have been enlightened.
So that's another really good channel. Veritasium.
Yeah, but I'm still freezing. I feel like I'm there. Oh, me too. Yeah, I'm barely holding on. I'm gonna meet for that issue.
Yeah, question?
So if you're colorblind, does that mean you're not like getting the same amount of waves, or are you just not?
That's a good question. So what if you're colorblind? You're getting the same light coming in, but the rods and cones in your eyes don't function quite the same as other people's do, and so some of the colors look the same to you. Yeah. 4 of my 5 sons are slightly colorblind.
Oh, wow.
Yeah, red, green. And so my oldest son, he's got this shirt. You know, have you seen those dot tests?
Yeah.
And they've got the different colored dots, and there's numbers in there. He's got this awesome T-shirt. It's got one of those on the front, and it says, "I can't read this," and he can't. It just looks like all one color to him. And I look at it, and I see, "I can't read this." It's really funny.
Yeah. Is there anyone colorblind in here? I want to test that. I don't think I know anyone's colorblind.
It does typically affect males more. Yeah.
I don't know anyone.
So my daughter and one son are not affected. My husband and I don't have any issues, so it's interesting. The part of this video I really love is the waves here, because we're talking about light waves, but we can't see how the waves are interacting. But here we can see how the water waves are interacting, and they're interacting in the same way that light waves do. So if this was our screen, we would see a bright patch and a dark patch and a bright patch and a dark patch and a bright patch and a dark patch. And so you see how the waves are overlapping and causing this constructive and destructive interference. Any other questions? The responses of the people at the beginning of this, really show you that, we go around using our eyes and looking at colors and doing all this stuff, and most of us really have no idea how it works, right? And then you start to think about it, and you're like, oh my goodness, it's kind of crazy. So this is a characteristic of a wave. You go through 2 slits like this, and you're going to get an interference pattern. That's going to become important later. So light behaves like a wave. Light also behaves like a particle. And this is demonstrated by the photoelectric effect. So it's been observed that many metals will emit electrons when a light shines on their surface. That's called the photoelectric effect. Classical wave theory says, well, the light energy is being transferred to the electron, and according to that theory, only the amplitude, the intensity of the light would affect the emission of electrons. So that predicts that if you used a dim light, there would be a lag time. You have to wait a while, shine the light, and wait a while for the energy to build up until there was enough to eject that electron. So here's an illustration of a setup. So we've got this piece of metal here, and it's in an evacuated chamber so that when these electrons are ejected, they don't just run into air, nitrogen and oxygen molecules. They've got nothing to hit, and they'll just travel through space to this positive electrode. We've got a voltage source here, so the ejected electrons are going to be attracted to the positive terminal. We can measure the electrons that are flowing here as current, and so we can see are electrons being emitted or not. So the light comes in here, it strikes the metal and causes electrons to leave the metal. So this is what actually is observed, not the prediction. So this is the rate of electron ejection as a function of frequency of light. So at low frequencies of light, no electrons are emitted. Doesn't matter how bright the light is, doesn't matter how long you wait, no electrons are emitted. When you get to a particular frequency, all of a sudden, electrons start getting emitted. That frequency will vary depending on the metal. So at that threshold frequency, electrons start being emitted. Here, the difference that we see between the higher intensity and lower intensity light is the higher intensity light will emit more electrons than the lower intensity light, but they both emit electrons. And if we go to higher frequencies, we don't get any higher level of electron emission. It just stays the same. So Einstein proposed that the light energy here was being delivered to atoms, to the electrons, in packets. So a packet of light is called a quantum or a photon. And those are words that come up in science fiction movies and literature and stuff, quantum and photon. So a photon is a piece of light. The energy that photon has is proportional to its frequency. We talked about the waves hitting you on the ocean, and if they're hitting you more frequently, there's going to be more energy. You're going to experience more force. So frequency has this symbol, this is a Greek letter nu. It looks a lot like an italicized V, but it's not. I will not try to trick you with that. E is energy. And so the energy is proportional to the frequency and inversely proportional to the wavelength. The symbol for wavelength is lambda. That's a Greek lowercase l. So, writing with white on white doesn't work. So lambda is a lot like an upside down W. Just flip the bottom up and you've got a lambda. So we could say that the energy is proportional to the frequency, or it's proportional to 1 over the wavelength. The proportionality constant, H, is Planck's constant, and this is its value. You don't need to memorize that. You don't need to memorize these equations either. I'm going to come back to that. So what's happening here is that one photon at that threshold frequency has just enough energy to eject an electron. A slightly lower frequency, not quite enough energy, the electron does not get ejected. So my favorite analogy for this is a child going to Disneyland. So let's just say it costs $100 to get into Disneyland, just because it's a nice round number. I think it's more than that now. So the kid goes, and he's going to go to Disneyland, and he's got $75. Are they going to let him in? No. Well, why don't they let him in for 3/4 of the day? He's got 3/4 of the admission price, because that's not how it works. You have the full admission price, or you don't get in, right? What if you have more than enough money? Will they let you in? Heck yeah. They'll take your $100 and you keep the rest of your money and you go in there, and then, if you've got $200, you've got $100 left, you could maybe get a soda and some French fries, right? That's about what it would cost. So here, the photon is the money, the amount of energy that's coming, okay? If it has the admission price, if it has the right amount of energy, the electron will be ejected. If it has more, the electron will also be ejected. But if it has less, no electron is ejected. So phi, it's the Greek letter phi, represents the binding energy of the electron. So that's like the admission price to Disneyland. That's the minimum amount of energy for anything to happen here. Well, what if we have higher frequency photons? Well, the electron's going to absorb the energy. It has to pay the binding energy, the admission price to Disneyland. And then what about the extra energy? Well, it has the rest of the energy, and that becomes the kinetic energy of the ejected electron. So remember, kinetic energy is 1/2 mv squared, the mass times the velocity squared. And so more kinetic energy means that that electron is going to fly away from the metal faster. Any questions about that? So the binding energy is the minimum amount to get any electrons ejected. So this shows that light behaves as a particle. Because if it behaves as a wave and you had lower energy waves, that energy could build up. But the light is coming in pieces, in packets, in photons. And that photon either has enough energy to eject the electron or not. And so when we get to this frequency, which corresponds to an energy, we have enough energy and we all of a sudden see a lot of electrons being ejected. We go to higher frequencies, the same number of electrons are going to be ejected because that's going to depend on the intensity of the light, how bright it is, but they're all requiring the same amount of energy to be ejected. The extra energy from that higher frequency light just becomes kinetic energy of the electron moving through space. Any questions? So light acts as a wave and light acts as a particle. So this is calculation we can do with those equations we just learned about. A 100-watt light bulb radiates energy at a rate of 100 joules per second. And this is in parentheses. The watt, a unit of power or energy over time, is defined as a joule per second. So what they're saying here is a 100-watt light bulb, 100 watts is the same as 100 joules per second. So that's one of the numbers they're giving us. And it says if all the light emitted has a wavelength of 525 nanometers, how many photons are emitted per second? It says use 3 sig figs. Well, we've got 100 joules per second, and we have a wavelength that's 525 nanometers. We could figure out what the energy of each photon is in joules. So that's using the equation hc over lambda. So h is Planck's constant, 6.626 times 10 to the minus 34 joules times seconds. C is the speed of light, 3.00 times 10 to the 8th meters per second. And the wavelength, again, we're going to want to put this into meters so that the units are going to work out. So 525 times 10 to the minus 9 meters. And then we see that meters cancel and seconds cancel. And what we've got here is the energy of one photon in joules. 6.626 times 10 to the minus 34 times 3 times 10 to the 8th divided by 525 times 10 to the minus 9th. It's going to be 3.7863 times 10 to the minus 19 joules. And that's the energy of one photon. So this light is giving off 100 joules per second. We can use this to convert between joules and number of photons, because one photon equals this many joules. So I put joules on the bottom and photons on the top. One photon, 3.7863 times 10 to the, didn't leave enough space, minus 19 joules. The joules cancel out. So I've got 100 divided by that amount of energy. Nope, did that wrong. 100 divided by that. 2.64 times 10 to the 20 photons per second. That's a lot of photons. Photons are really tiny. Any questions? This is one of those problems where, we learned about this equation, so it's fairly straightforward to do that, but then you have to do something else with it as well. And so that becomes a critical thinking problem. Come on. There we go. Arrange these three colors of visible light, red, green, and blue, in order of increasing wavelength, frequency, and energy per photon. So I'm going to show you how you can do this without having to memorize the electromagnetic spectrum. Personally, I find it difficult to memorize a picture, right? There's all these things in there. So if I needed to do this question, this is where I would start. I would say, okay, Roy G. Biv, that's my visible light, right? And then there's infrared light and there's ultraviolet light. Well, guess which one is next to violet? Ultraviolet, because it's extra violet, right? It's ultra. So we've got UV over here. It makes me think of Ultralord. And here's red, and lower in energy than red is IR, infrared. Okay, so that helps me to remember which color has more energy and which has less energy. So this is high energy on this end and low energy on that end, because I know very well that UV light gives me a sunburn. Right? UV light is higher in energy. Are we getting sunburn from the light, the visible light in this room? No. But you go outside, the sunlight has UV light in it also, and you stay out there too long and you're going to get a sunburn. So the UV end is the high energy. You think you can remember that? Yeah. So that's high energy. So the next thing I'm going to do is I'm going to draw two pictures of waves. And so here's my wavelength, right? The distance between the waves. And then which of these has more energy? The top one or the bottom one? The bottom one. Well, is there something special you have to remember? I just look at those and this one looks like it has more energy, doesn't it? It's jumping up and down, and this one's going, okay. High energy, low energy. So this one's high energy, and that one's low energy. So high energy corresponds to short wavelength. So at this end we have short wavelength, and the low energy corresponds to long wavelength. Frequency and wavelength are opposite of each other. So if this end is high frequency, it must be, high wavelength, it's low frequency. And if this one is low wavelength, it's high frequency. Okay, now let's look at the question. They're asking us about red, green, and blue light. And they want us to put them in order of increasing. That means start with the thing that has the smallest. So for A, I want the color with the smallest wavelength to the one with the highest wavelength. Well, over here, the larger wavelength is on this end, right? Smaller wavelength is on that end. So which color has the smallest wavelength? And it's not red. This end is smaller wavelength. So here I've got red, green, and blue. Which is closest to this end? Blue. So blue is the shortest wavelength. And then what's next? The green. And then what has the longest wavelength? The red. Okay, what about frequency? Well, this end was low wavelength and high frequency. So this end's high frequency, that end's low frequency. I want to go from low to high, so I'm going to start at this end. So that's going to be red to green to blue. Are there any of these that are going to result in like green to red to blue? No, green is always going to be between the other two colors. How about energy per photon? It's the same as the frequency. Because this end is low frequency is low energy. And so here's another question. Put them in order of speed. This is a trick question. They're all the same. Yeah, they're the same. They all travel at the speed of light. Yes?
So E goes with wave, V goes with frequency, or is it?
Energy and frequency are directly proportional. So high energy is high frequency. You think about, getting pounded by waves at the beach, right? If they're coming at you really fast, frequently, that's going to knock you over as more energy. And wavelength and frequency are opposite because the waves are all traveling at the same speed. So if these are traveling at the same speed, then this one is going to have waves pass a point more frequently than that one. So the frequency is larger, but the wavelength is shorter.
So is the photon, like, I'm just wondering which variable for the photon?
It's the energy.
The photon is the...
So the photon is is a particle of light. And so if we left off per photon, the answer would be the same. Which light has more energy? So don't get thrown off by photons being stuck in there. Any other questions? Okay, back to the photoelectric effect. Suppose a metal will eject electrons from its surface when struck by yellow light. What will happen if the surface is struck with ultraviolet light? So we need to know which of these has more energy, right? Which of these is equivalent to more money trying to get into Disneyland? The yellow light has enough energy, enough money to get into Disneyland, enough energy to eject electrons. If we have light that has more energy, will it eject electrons? Yeah. If we have energy that's less, light with less energy than yellow, will it eject electrons? No, it won't. So what we need to know is ultraviolet have more energy or less energy than yellow? More. Ultraviolet can give you a sunburn. Yellow light can't. So this light has more energy than the yellow. So will it also eject electrons? Yeah. So let's look at these choices then. It says no electrons would be ejected. Oh, no, that's not true. So the rest of these are all really similar. Electrons would be ejected. They would have the same kinetic energy, greater kinetic energy, or lower kinetic energy. They're going to have greater kinetic energy. The light that's coming in has more energy than needed to eject the electron. So the electron goes away with more kinetic energy. Question?
So with the little diagram that we drew in the other slide, I assumed that the order of colors corresponded with low to high energy, but it's not.
No, it does.
Oh, well, I was seeing the wavelength. Right,
Yeah, it's very confusing. Yeah, and that's why I don't even try to remember which is highest or, especially the wavelength thing. The energy one is the one that sticks with me, probably because I've gotten a lot of sunburns in my life. You can imagine. So ultraviolet, higher energy. So that tells me that the violet end of Roy G. Biv, high energy. And then from that, I figure the other things out. Yeah. So, next exam, I'll give you a piece of paper with equations and periodic table and stuff on it. Might be a good idea to draw a little diagram like I did on the previous page before you read any questions, because what happens when you read the first question? Sometimes your mind goes blank, right? So before you look at the test, you can write stuff down on the paper so that when it disappears from your head, you can read it, right? So sometimes light behaves like a wave, the double slit. Other times, light seems to act like a particle, the photoelectric effect. And which behavior you observe depends on the experiment.